Hi guys, welcome back to my channel, and this is the second video in the AtCoder DP contest series. This problem is very similar to the first problem in the problem set, so I would suggest that you first solve problem A and then really try to figure out how to do B. It should be relatively simple to do B once you figure out A, but here's the editorial anyway. So, to recap on the problem, you have n stones, and from stone I, you can jump to stone I plus 1, I plus 2, up to I plus k, and k is given in the input. Now, every time you make a jump, the cost is the difference between the height of the stone you jumped from to the stone you ended up jumping to. And you just want to find the minimum total cost incurred before it reaches stone n. So let's look at this first sample input. Okay, so here our k is 3, so from anything I, we can jump to 1, we can jump to I plus 2, and we can jump to I plus 3. So how do we find the minimum cost incurred to get to 2? Well, let's take 4 as an example. What's the minimum cost to get to 4? Because this has limited examples. So there's only a couple ways to do this. Either you can go from 10 straight to 4, or you can go from 10 to 30 to 4. Those are your only options. So which one's better? Well, going from 10 to 4 is a cost of 30. And going from 10 to 30 is 20. And if we add that to going from 30 to 40, we get 30 again. So it turns out here, both options of getting to 40 are the exact same, which is 30. So 30 is the minimum cost to get to 40. So how do we calculate this efficiently for every single value here? As you can see, every single time you add an element, the number of options to get there grows exponentially. So we have to do something clever. So let's say we've already calculated, let's assume at first that we know the minimum cost to get from 10 to get from the beginning to 10, beginning to 30, and to get from the beginning to the third stone, which has a height of 40. So for the first one, it's 0, for the second one, it's 20, and for the third one, it is 30. So given this information, how do we calculate the minimum cost for 50? Well, because it's 3, any of these from any of these 3 stones, you're able to jump to 50. So all we have to do is calculate the minimum of these costs, which are the cost to get to the stones 1, 2, or 3, plus the cost to get to any of these stones to 50. So if you want to go straight from the beginning, the cost will be 40. And if you want to go from the second stone, the cost will be this 20 here, plus the difference between 30 and 40, which is also 40. And then from 40 to 50, it's a jump of cost 10 plus the 30, which is already incurred from getting to 40. So then that will also be 40. So in this case, again, the minimum cost to get to 50 is 40. So now let's look at 20, which is where it gets a bit more interesting. Here you can get to 20 from 30, 40, or 50. So getting from 30, which is from stone 2 to stone 5, that is a cost of 20, which is the total cost will be 20 plus 10. So 10 is the cost to get from stone 2 to stone 5, and 20 is the cost to get from the initial stone to stone 2. Same thing, from 3 to 5, it's 30 plus 20, and from stone 4 to stone 5, it's 40, which is the minimum cost to get to 50, plus 30. So now here, the minimum cost to get to the last stone is 30. So you might be seeing a pattern. If for each stone we store the minimum cost to get there, then each stone here, all we need to do is query k values from this min cost, and that'll allow us to calculate the minimum cost to get to this stone very easily. So to put that in a DP relation, dp of I is equal to the minimum of dp I plus 1 plus the cost to get from stone I plus 1 to stone I, or sorry, it'd be I minus 1, all the way to dp of I minus k plus the cost. So as you can see, this is very similar to the solution for A, except there's just more options. Now, if we look at the constraints, this works perfectly because for each n, we just have to query k values from the DP. So now let's look at the code. The code, again, is doing this in reverse. Instead of doing it from I to I minus 1 and I minus 2, I minus 3 to k, we calculate for I being the initial stone, how does this affect the k stones in front of it? So, as you see from each stone, we go to the stone I plus 1, I plus 2, up to I plus k. And to make sure there's no errors, we make sure that this value doesn't exceed n. And we simply do the minimum of what the min cost to get to I plus j is currently, which is stored in dp, from what that value would be given that we come from stone I. And this is a solution. It's very nice and neat with DP. Okay, I hope you guys liked this video and found it helpful. Stay tuned for the rest of the DP editorials. And if you liked the video, please like and subscribe. I'll see you next time. Bye.